Okay, welcome back to Chapter 8, and we're talking about angular momentum and its conservation. And in the last video, I had already started talking about this concept that just like with linear momentum in an elastic collision is conserved, angular momentum is also conserved. And in this slide, we're going to essentially prove that mathematically. So we already derived this formula in a previous video. It's basically rewriting Newton's second law of motion, which in linear terms we know is F equals ma. Changing that over to rotational motion, it's the sum of torque equals I. So that's moment of inertia times angular acceleration. So if we look at angular acceleration, its definition is the change in angular velocity with respect to time. And we can rewrite the change in angular velocity by saying it's the final velocity minus the initial velocity, or omega minus omega naught. So what we can do is take this term right here, which is equal to alpha, and substitute it into this equation for alpha. So now this equation is the sum of torque equals the moment of inertia times angular velocity minus initial angular velocity with respect to time. If we distribute that moment of inertia, I term, across the numerator, it now becomes I omega minus I omega naught. Okay? And if we recall our definition of angular momentum, or low-momentum as some of my students call it, that's equal to moment of inertia times angular velocity. So what we're saying here is this is the final momentum, and this is the initial momentum. So the sum of torque is equal to L minus L naught over delta T, or it can be simply written as delta L over delta T. So this is essentially Newton's second law of motion written for momentum, in terms of momentum. Okay, and again, when an outside force is absent, when we have the total sum of torque being 0, then angular momentum is conserved. So this is, if we think back to Newton's law that says that an object in motion will stay in motion unless an outside force acts on it. That's what this is saying, that the momentum will continue, that the final momentum will be equal to the initial momentum as long as we don't have some outside force acting on it, like friction or air resistance. So if we ignore those things, momentum is conserved. So some situations where we can change the moment of inertia and yet conserve momentum is like when a figure skater is spinning around and her weight is distributed farther away. The weight of her arms is distributed farther away from the axis of rotation. And then when she pulls her arms into her chest, that weight or mass is no longer as far away from the axis of rotation. So she has reduced her moment of inertia. But in order for the momentum to remain constant, if the moment of inertia is reduced, then the angular velocity will have to increase. So by decreasing her moment of inertia, she increases her angular velocity. So that's why she spins faster. And the same with a diver. When the diver tucks her legs in closer to her body, her rotational velocity, omega, increases. And the same is true if you've played on a tire swing before and you've had your legs out and you're spinning around in a circle. When your legs are out away from your body, you spin more slowly. And if you tuck them in, you'll spin more quickly. And we've got just another image of a figure skater there doing the same thing. So let's look at an example here where we have a clutch that consists of two cylindrical plates. So we have basically one plate on an axis and another plate above it. And the one plate is going to be spinning, the other one is going to be stationary, and then they're going to be pushed together. And they'll interlock with each other due to friction or some type of mechanical grip between the two. And this rotating cylinder is going to then cause this one to rotate as well. They're going to be locked together. This is sort of like the example we did with the two train cars when we were talking about linear momentum. When one train car backed into another, they became linked together and then acted as one long train car that moved down the track. This is a similar example, but using angular motion. We have one spinning clutch plate that's going to come into contact with another. The two will become one and then spin as one. So the two masses in this example are not the same, like they were in the train example. We have a mass of 6 kilograms and a mass of 9 kilograms, but they each have the same radius of 0.6. So the first plate we're going to accelerate from rest to an angular velocity of 7.2 radians per second in a time period of 2 seconds. We want to calculate the angular momentum of plate A all on its own and the torque required to accelerate plate A. So our formula for angular momentum, L, is equal to I omega. And so I for this disk, since it's a cylinder, is 1/2 mr squared. So that's 1/2 mr squared and multiplied by our angular velocity. So the mass was given as 6.0 kilograms. The radius was 0.60 meters squared. And once this gets sped up to its top speed, that angular velocity was 7.2 radians per second. So that is equal to 7.8. Now we've got some derived units here for momentum. It is kilogram meter squared per second. The radians just kind of fade into the background. So that is the angular momentum of plate A. This one that is spinning before it is pressed up against plate B. Okay, so that's the first part of our problem, is to find the angular momentum of plate A. It's 7.8 kilogram meters squared per second. Now let's calculate how much torque was required to get it up to that speed. So we had come up with this equation in a previous slide that torque is equal to the change in momentum over the change in time. So this is basically Newton's second law of motion in terms of angular momentum. And so our change in momentum, since the initial momentum was 0, it started from rest, and we calculated in the previous slide that when it reaches its top speed, it has a momentum of 7.8 kilogram meters squared per second, and we're going to divide that by 2.0 seconds. That gives us 3.9. It looks like kilogram meters squared per second squared, but if you'll recall a Newton, since a Newton is a kilogram meter per second squared, these units become, this is equal to 3.9 Newton meters, which is our unit for torque. So the torque that was required to accelerate this plate up to this angular velocity was 3.9 Newton meters. Okay, so now we're finally to the point where we have this plate A that is spinning. We're going to press it up against B. Then they're going to rotate as one unit, and we want to know what that new angular velocity is going to be. So here's where we're going to use our conservation of momentum. So the angular momentum is equal to moment of inertia times angular velocity. So what we're saying here is the moment of inertia of plate A times the angular velocity of plate A is going to be equal to the momentum after they come together. So they're going to come together, and their moments of inertia are going to combine. We'll have a moment of inertia A plus moment of inertia B, and then that's going to be multiplied by their omega 2, their angular velocity after they've come together. So the angular velocity 2, which is what we're trying to find, how fast will it be spinning after the two plates come together, is equal to IA omega 1 over IA plus IB. Yeah, that's it. So what do we know here? What can we plug in? So for these cylinders, the moment of inertia is 1/2 mr squared. And I don't know that we ever calculated this. We had it included in another formula. So if we just look at the moment of inertia for plate A, that is 1/2 times 6.0 kilograms times its radius of 0.60 meters squared. So moment of inertia for A is equal to 1.08, and moment of inertia B is going to be 1/2 times its mass was 9.0 kilograms, and it has the same radius of 0.60 meters squared. So the moment of inertia for cylinder B is 1.62. So our omega 2 is going to equal 1.08 times angular velocity 1 was 7.2 over 1.08 plus 1.62. And that equals 2.88 or 2.9 radians per second when rounded to two significant figures. So that is the final angular velocity when these two plates come together and act as one. So that brings us so close to the end of Chapter 8, but I do still have one more concept to talk about briefly. I don't think I'm going to get to that in this video, so I'm going to have to make one more short video to finish off Chapter